We want to determine the residence time distribution when we have a number of CSTRs in series, and we're going to do that by solving mass balances for a tracer, and this will be a pulse tracer that we inject to the first CSTR in the series. And so at time equals 0, we inject a pulsive tracer into the first CSTR, and that means we're not adding any more tracer after that, so that C0 concentration coming into the first CSTR is 0. We'll call this C1, and of course concentration leaving the first CSTR is the same as the concentration in the first CSTR. C1 now is the concentration entering the second one, so C2 is leaving, C3, and then Cn for the nth CSTR. And so we're going to set up the mass balance for the first CSTR. We have the volume of the CSTR. Each CSTR has the same volume. The change in the concentration in the reactor, C1 is the same, of course, as that leaving. The volumetric flow rate, this is liters per second, for example. The volumetric flow rate times the concentration entering, the volumetric flow rate times the concentration leaving. There's no reaction for the tracer. So this is the complete mass balance. And then we know at T equals 0 that we've already we injected a tracer. So if you like, at T equals 0.0001, we have the concentration inside the CSTR is some initial concentration, which is a function of how much tracer we inject. So to solve this mass balance, remember this is 0, and so we can separate variables to solve this. And then once we separated variables, we're going to integrate from time equals 0 to some later time, integrate from the initial concentration to the concentration at some later time. And so the left side, if we integrate, we get a log C1 over C initial. The right side, first I'm going to write this as the integral of dt over tau. So tau is the space-time, volume over the volumetric flow rates as units of time. Tau is the same for each reactor, the residence time in the reactor. Now I do the integration on the right side. It's T over tau, which means the concentration leaving the reactor is the initial concentration and this exponential decay. We inject tracer in the first reactor, then the concentration exponentially decays as a function of time. So now I want to do the same thing for the second reactor, and the difference is there is tracer flowing into the second reactor. So the change in the concentration in the reactor, C2, is the volumetric flow rate times what's flowing in, C1, the volumetric flow rate, what's leaving. Of course, we just calculated C1. Now I can rearrange this equation and also substitute for volume over volumetric flow rate in terms of tau. And where now I need initial conditions for reactor 2, and that's at T equals 0, C2 equals 0. We've injected tracer into the first reactor only, so there's been no time for tracer to get into the second reactor. Now we can solve this differential equation using an integrating factor. I won't go into explanation. You can find explanation of integrating factors elsewhere. We're going to use e to the t over tau as our integrating factor. And then we know from differential equation solutions, we can write the concentration C2 as this integrating factor times now the right side of the equation, integrating this respect to dt, and then there's going to be an integration constant, and it's going to be divided by our integrating factor. We can solve for C2. I'm going to bring the term in the denominator, And I do the integration, you notice I have e to the plus, tau over 2 e to the minus. So these cancel. I have C initial as a constant, so I just end up with t over tau plus my integrating factor. And now I apply my initial conditions. When t is 0, the first term disappears. C2 is 0. This means my integrating constant for this solution is also 0. So I have C2. I can now do the exact same balance for the third reactor, where there's no concentration of tracer in the third reactor, time equals 0. So the initial condition, t equals 0, C3 is equal to 0. The feed to the third reactor is concentration C2. I won't go through the details. I'm just going to write them down so then you can go through them at your own speed. And so here I've worked through the exact same type of solution. Notice the difference now, because I have t here inside the integral sign, I end up with t squared over 2. And so if I write the balance now for the fourth reactor, I'm going to end up with t cubed over 3. And so it looks like this. So here's concentration of the fourth reactor. And then the general Cn is this initial concentration, t to the n minus 1, e to the minus t over tau. You can see for the fifth reactor we'd have 4 times 3 times 2. So this is going to be n minus 1 factorial. And we have tau to the n minus 1 also. So not quite finished. We now have the concentration from the nth reactor. We want the residence time distribution, and so we have to normalize, and we can look at the first reactor to do this normalization. The normalization we're going to do is that the integral of the residence time distribution, or sometimes referred to as the exit-age distribution, from 0 to infinity should equal 1, because essentially this is a probability of leaving the reactor. All the probabilities should add to 1. So that means the integral of C1, which is this initial concentration, tau, if we want to normalize this and make it equal to 1, we would essentially say C1 divided by some constant alpha now is going to equal 1. And then what we're saying is C1 over alpha is our residence time distributions. So we're going to do this integration, C initial over alpha, integral of e minus t over tau divided by minus 1 over tau. Evaluate between our limits is equal to 1. Then we can substitute in the limits. We're going to have minus tau, C initial over alpha, e to minus infinity is 0, e to the 0 is 1, so it's minus 1. This is equal to 1. This says alpha is just tau times C initial. Remember what I did was divided C1 by alpha to get e of t. So e of t was just C1 over alpha. C1 was the initial concentration, e to minus t over tau. Alpha was C initial times tau. So the residence time distribution for the first reactor, e to minus t tau divided by tau. And then for each of the others, I would also divide by alpha. So my general residence time distribution, E for the nth reactor, is going to divide this by alpha. So the C initial is going to cancel. Have my exponential term, factorial, and I have an additional tau, so now I have tau to the nth. And so this is the residence time distribution for any CSTR in the series of CSTRs, where we have tau as the space time, the resonance time in a given CSTR. All the CSTRs are identical.